Hello and welcome. We're going to solve this problem together. But first, I think you should pause the video and try it on your own. I think you can get much farther than you might realize. Okay, so let's start by reading this together. It says a sequence of transformations. So that's a sequence, of course, is an order of transformations. So a bunch of them, we're going to do a bunch of transformations, and we're doing them one after the other. So a sequence of transformations was applied to an equilateral triangle in a coordinate plane. So that means you've got our x and our y, and somewhere on this plane there is an equilateral triangle, a triangle where every side is exactly the same. We'll call that triangle E. The transformations were rotations, so we're turning that equilateral triangle one way or the other. Okay, I'm just thinking, okay, it's going to turn the triangle, but it's not going to change it, it's just going to turn it. Reflection, that means we're reflecting it across some line, maybe the x-axis, the y-axis. We'll get a mirror image of it somewhere else, and that won't change its angles or side lengths. And translations, I look at the SL in translation, that means slide. We're going to take the shape and slide it down or over or up or to the right. We're going to slide it around. So it's the same shape, just slid around in some direction. And they want to know which statement is true about the resulting figure. So when we take our original equilateral triangle and we turn it or we reflect it and slide it over, what's going to be true about it? Well, I know the angles are going to be the same. We're not messing with the angles, and the side lengths are going to be the same. We're not messing with those. It's just going to be somewhere else on the coordinate plane. So let's look at that. A, it must be an equilateral triangle, so far that's so true, with the same side lengths as the original triangle. Well, yes, that's true. We're not changing the side lengths, right? I think that's the answer, but let's keep going. It must be an equilateral triangle, but the side lengths may differ. Well, the only thing that would change the side lengths, this will only happen if we're using a dilation. A dilation is when we multiply each point by a certain scale factor, which then enlarges each side by a certain amount. The angles aren't changed, but the size is changed, and I'll show you an example in a moment. But that's not true here. We're not dilating. It may be a scalene triangle, and all the side lengths may differ from the original triangle. Well, none of the transformations, rotations, reflections, or translations, or dilations will change the shape of a triangle if we apply those transformations to all the points. And that's kind of what we're doing at this level. We're applying a rotation, reflection, and translation and dilation to all points, not just part of the points of a shape. So we're not going to change the angles. In fact, the angles won't change at all. Equilateral, of course, means every angle is the same, and scalene means every angle is different. So this can't be true, right? An equilateral triangle has all 60-degree angles. Scalene has all different angles, and the angles aren't going to change. So that's not true. It may be an obtuse triangle. That's a triangle with one angle over 90 degrees, but that's not going to happen either, right? We're not even going to change the angles. That's not going to be true. But let's just extend this conversation. I'm going to use GeoGebra here to any triangle. So I just made some triangle up here. And let's just take a look at what translations look like. So I'm going to turn on my translation triangle. Now initially we're not translating it at all, but then if I move it up or down or left or right, you can see it's the same triangle, right? However I translate it, just in a different location. It's just an image of itself slid in some direction. So that's what a translation looks like. Let's look at a rotation. So rotations are often the scariest, I think, but you have to realize that when you look at this, that all we're doing is taking our triangle and turning it around some point in the plane. In this case, I'm turning it around the origin. Notice it's still the same triangle. I can turn it right back onto itself. All the angles match up and everything. But here, we can see that rotation won't affect the side lengths or the angles, just the position. Same is true with reflection. If I reflect across the x-axis, that's this triangle down here, it's being reflected across the x-axis, or this triangle here reflected across the y-axis. I mean, sure, many of the locations of the angles change. Like, for example, this angle here, angle BAC, is on the left side of the triangle. Then when we reflect it, we get a mirror image. So now it's here. BAC is this angle on the right side of the triangle. But there's still the same triangle in terms of angles and side lengths. The only thing that will change the side lengths is dilation. So dilation is just when we change our shape by some scale factor, and it goes upside down here. We multiply by negatives, which is really cool. It goes to a point, nothing, if multiplied by 0. It's smaller than the triangle until our scale factor reaches 1. This is my scale factor here, k. K is a half. And notice our triangle, each side length is the half of the original. When k is 1, it's the same triangle. And then as we increase k, right, to 2, each side length is essentially double its original. And this might look a little overwhelming. Let me just shift over. But essentially what's happening here is that if you want to draw a dilation at this point, we're dilating around the origin, all you have to do is take each point and multiply it by your scale factor. So for example, A is 1, 1, K is our scale factor 2. So to get our new point with a dilation of 2 around the origin, I just multiply 1 and 1 by 2, and I get 2, 2. That's this point here. I multiply 8, 2, point C. I multiply 8 and 2 by 2. That's our scale factor, so I get 16 and 4. And 4 and 6 times 2 gives us 8 and 12. So this is our new triangle here. And that will give us a triangle where the angles are the same, but the side lengths grow by the scale factor. Alright, I hope this helped.